Hello YouTube. In this video we're going to examine the views of Emil Lakatos. As a bit of background, Lakatos was a great admirer of Karl Popper. He sometimes saw himself as providing a more sophisticated development of Popper's falsificationism. At the same time, Lakatos felt the force of Kuhn's appeal to the history of science. We saw in the previous videos that Kuhn seems to suggest, on the basis of historical cases, that science is generally a non-rational process. At least the big changes in the history of science, such as the Copernican revolution or the Darwinian revolution, these were analogous to religious or political conversions. Now, just like Popper, Lakatos found this kind of view appalling. He wanted to show that despite the historical arguments raised by Kuhn, there is still a rational methodology for science. The basic claim of Lakatos' theory is that science is organised into what he calls research programmes. Research programmes are somewhat like Kuhnian paradigms, but as you'll see, there are important differences. A research programme is a sequence of theories in some field of science. Change from one theory in a research programme to another, Lakatos calls a problem shift. Research programmes have a hard core of theory. And this hard core usually consists of certain fundamental principles or laws which cannot be changed in problem shifts. The hard core is not tested directly when scientists make observations. Instead, scientists try to work out how the hard core can be made compatible with observation. As Kuhn argued then, there is a substantial degree of dogmatism in science. Scientists accept the hard core dogmatically. They're reluctant to give it up. Indeed, it's often not possible to derive empirical predictions from the hard core in itself. With Newtonian mechanics, for example, the hard core consisted of Newton's 3 laws of motion plus universal gravitation. No observation could falsify this because in itself it makes no predictions whatsoever. It's compatible with all possible observations. In order to derive any predictions from these laws, you need to specify the objects in the universe and their properties. You need auxiliary hypotheses. So research programs have a protective belt, which consists of various auxiliary theories that connect the hard core to the data. The auxiliary theories use the hard core to make empirical predictions. In the case of Newtonian mechanics, the protective belt consists of various claims about, say, the structure of the solar system and the properties of the planets. Only the protective belt is tested against the data, and the central goal of working scientists is to preserve the hard core by altering the protective belt, which is shown in this diagram here. The protective belt is used to connect the hard core to the data, and when predictions are falsified, the protective belt is altered and the hard core is retained. So, one way to think about this is that when scientists make an observation that conflicts with their theory, they face a modus tollens argument. So, the first premise is, if hard core plus protective belt, then we'll make observation O. The second premise is not O. So, you do the experiment or the observation and it turns out your prediction was wrong. You conclude from this, therefore, it's not the case that the hard core and the protective belt is correct. But we face a choice of which of these conjuncts to reject. We can reject the hard core or we can reject the protective belt. Research programs embody a negative heuristic, which instructs scientists not to modify the hard core. Modifications are made according to a positive heuristic, which gives scientists guidance. It gives them suggestions or hints on how the protective belt should be changed. Now, Lakatos doesn't give many details on what the positive heuristic actually is, but it's maybe similar to Kuhn's ideas of exemplars. Right? There are certain specific achievements that scientists try to use as a model for further research. Obviously, this will be different for different research programs. For example, when the orbit of the planet Uranus was found to deviate from the predictions of Newtonian mechanics, the negative heuristic instructed scientists not to alter the basic Newtonian laws. If you change Newton's laws, you abandon the entire Newtonian research program. As for the positive heuristic, scientists knew that gravitational attractions between the planets could alter planetary orbits, and they knew from the discovery of Uranus that there could be planets that couldn't be seen with the naked eye. So it made sense to postulate another planet beyond Uranus. Furthermore, postulating another planet beyond Uranus was something that was easily testable, because you can easily go out and look for that new planet. You can look through your telescopes and see if it's there. There are plenty of other changes scientists could have made to the protective belt. For example, they could have just assumed that, well, for some reason telescopes don't work properly when viewing objects that are very, very far away. Right? So that's why Uranus doesn't seem to fit the Newtonian predictions, because our telescopes are just giving us the wrong information for some unspecified reason. But obviously it's not clear how to use that idea to develop Newton's theory in any interesting ways. So the positive heuristic tries to guide scientists to make changes to the theory that will be fruitful for further research, that will make new predictions. Let's see how this works in a couple of other cases. A good example might be the development of continental drift. The hard core of the continental drift program was the claim that the continents have moved over time. So continents that were once combined are now separated and vice versa. And this movement of the continents explains various biological and geological features that we see in the modern world. We find that as this program developed, different theories were proposed of the exact nature of this movement. Alfred Wegener, who first proposed continental drift, argued that the continents literally moved through the sea floor. And it was very difficult to explain how this could happen, because it was known that the continents are less dense than the sea floor. There were also no known forces that would have been powerful enough to cause entire land masses to move. Wegener initially appealed to the fact that the rotation of the Earth causes the Earth to be slightly flattened. The Earth isn't a perfect sphere, but is bloated slightly along the equator due to its rotation. And this introduces differential gravitational forces, which Wegener thought might push the continents. This kind of force does exist, but it's far too weak to cause continental drift. So, over the decades, different theories were proposed of the mechanism of continental movement. The modern view is that the Earth's lithosphere is divided into gigantic plates. Both the continents and the seafloor sit on top of these plates, and the seafloor itself spreads outward, as shown in this diagram. So you can see that we have sort of plates here and a plate here, and the seafloor sits on top of those plates. As those plates move apart, the seafloor and the continent are both pushed to the right. So this appears to be driven primarily by convection currents in the mantle. As you go deeper into the Earth, the temperature rises. Hotter rocks have lower density than cooler rocks, which means the hotter rocks rise while the cooler rocks sink. So you get this circulating pattern which flows very slowly over millions of years. However, there's still some debate about how exactly convection currents cause plate movement, and some geologists question this standard convection theory. Perhaps tidal forces due to the influence of the moon play a larger role. This is all part of the protective belt, but the basic principles of continental drift are not questioned. The basic claim that the continents have moved and that we can explain certain geological and biological features, these have remained fixed. And this example illustrates an important point. Recall that Kuhnian paradigms monopolize a field. All scientists adopt a single paradigm. Kuhn literally defined normal science as science that takes place under a single paradigm. Well, unlike paradigms, different research programs can compete in the same field. And Lakatos thinks that competition between research programs is a really important part of scientific progress. This is a crucial difference between Lakatos and Kuhn. And we see this in the case of continental drift, because for many decades there were, broadly speaking, two other research programs competing against drift. The contractionists held that the Earth has been contracting as it cools. Continents may have moved to some degree, the general face of the Earth has changed, but this is simply due to the contraction of the planet. The permanentists held that the Earth has retained the same size and the continents have been fixed. And these research programs flourished simultaneously for many decades. And so scientists often have a choice of what research program to adopt. Another good example is Darwinism. The hard core of the Darwinian research program is the claim that natural selection explains the origin of species and adaptations. So natural selection explains complex sophisticated traits like the eye or opposable thumbs. Natural selection occurs when three conditions obtain. First, there is variation of the traits in a population. For example, some butterflies are red and others are green. Second, there is heredity. So the variations are passed from parents to offspring. Green parents have green children and red parents have red children. Finally, differential reproduction. Different traits can increase or decrease your chances of reproducing. If you imagine a forest of mainly green leaves, the butterflies that have green wings will be camouflaged against the green leaves, so they won't be eaten by predators. So the green wing butterflies will have a greater chance of reproducing than the red wing butterflies. If those conditions obtain, you get natural selection. And the Darwinian research program treats natural selection as a central force of evolution. It claims that selection is what explains the origin of complex structures. Now, Darwin was heavily influenced by Charles Lyell, who pioneered the uniformitarian tradition in geology. The basic claim of uniformitarianism is that the processes at work in the past are the same as those at work today. So to explain how geological structures are formed, we should appeal only to those processes that we can currently see in operation, such as sedimentation, volcanic eruption, water erosion, and so on. If you extrapolate these processes over millions of years, you get the structures that we see. So, water erosion extrapolated over millions of years will create massive valleys. And Darwin applied the same view to evolution. The environment and the biological populations inhabiting it change very gradually, and the biological processes occurring in populations are the same today as they were in the past. This uniformitarian claim formed part of the protective belt of Darwinism. Today, we to some degree reject uniformitarianism. We now recognise that there have been sudden catastrophic changes in Earth's history. There have been ice ages and supervolcanic eruptions and asteroid impacts, and these radically and rapidly change the Earth's climate and cause mass extinction events and so on. Similarly, over the past century, we've seen changes in ideas about the nature of inheritance, the mechanism of speciation, the mathematical tools used in fields like population genetics, like the applications of game theory, and so on. All of this has built up a robust protective belt around Darwinism. But the hard core of natural selection as the central evolutionary force that explains the origin of complex traits, this has remained unchanged. Lakatos classified research programs as either progressive or degenerating. The basic thought here is that in progressive research programs, new theories are improvements on the older ones, whereas degenerating programs don't exhibit improvement. So you want your research program to be progressive. Three features are exhibited by progressive research programs. First, each theory in the sequence incorporates most of the successors of the former theory. When the Newtonians postulated an eighth planet, they were still able to accurately predict the orbits of the other planets. So the new theory inherited the successors of the older one. Second, each theory in the sequence makes more predictions of novel or surprising facts than the last one. Obviously, the postulation of an eighth planet is itself a novel prediction, a prediction that we wouldn't otherwise have any reason to expect. And even better, the Newtonians were able to use the deviations in Uranus's orbit to work out exactly where the eighth planet should be observed. So that was a really powerful prediction. And third, some of those novel predictions should be shown to be accurate. And of course, this happened with the eighth planet. Astronomers looked to where their theory predicted it should be, and they quickly found it. So, modifications to the protective belt must generate new predictions, and some of those predictions must be confirmed. If the problem shifts of a research program do not exhibit these features, right? If the research program resolves anomalies by just introducing ad hoc hypotheses that don't produce new confirmed predictions, then it's said to be degenerating. And this is what happened with Marxism, for example, according to Lakatos. The predictions of the Marxists systematically failed. For example, they predicted that the socialist revolution would occur in the most industrially developed society, but it actually happened in Russia. And they came up with ad hoc hypotheses that, to explain these failures, but they didn't make new predictions. Or at least any predictions they did make weren't confirmed. Marxists didn't see an increase in predictive power. Of course, this is all very similar to Popper's ideas. And certainly, as I said, Lakatos was inspired by Popper. But Lakatos, unlike Popper, provides some insight into when it's acceptable to introduce ad hoc hypotheses to explain away anomalies. Lakatos says you need to use anomalies as opportunities to increase theoretical and predictive power. Lakatos provides an answer to the demarcation problem. This is the problem of what is it that demarcates science from pseudoscience. And Lakatos says good science is a progressive research program. Bad science is a degenerating research program. If the degeneration continues over a very long time, the research program will become pseudoscience. An important point to note here is that in a degenerating research program, every successive theory might still be falsifiable. Indeed, every theory might make very bold, surprising, striking predictions, just as Popper required. But Lakatos says that's not enough. At the very least, increasing numbers of those predictions need to be confirmed. We need to have confirmed predictions. So Popper and the falsificationists were wrong to think that falsifiability demarcates science from pseudoscience. Plenty of pseudoscience is falsifiable. Science needs more than just falsifiability. Conversely, of course, we've already seen how, on Lakatos's view, the hardcore of the research program is not really a candidate for falsification, so falsifiability isn't necessary for science either. For Lakatos, scientific status is determined partially by history. Indeed, on Lakatos's view, it's not really a specific theory that's labelled scientific or pseudoscientific, but rather a series of theories. You have to consider how the research program has developed over time. Now, as Popper suggested, scientists do attempt to find problems with accepted theories. Once a research program has been developed, this may be their primary focus. They might focus just on trying to knock down the accepted theories. So there's a strong falsificationist influence on Lakatos there. But the point is that having attained a falsification, having attained that piece of recalcitrant data, the scientist tries to alter just the protective belt. They try to retain the hard core in such a way as to produce new confirmed predictions. Remember, Popper thought that confirmation wasn't really important, and that because he was inspired by Hume's arguments against induction, he thought that confirmation didn't matter. But Lakatos thinks it does. He thinks it's very important to have increasing confirmation. So although Popper was a big influence on Lakatos, there are also some really important differences there. Okay, let's turn to some problems for Lakatos. Regarding the distinction between science and pseudoscience, one worry is that on Lakatos's theory, it seems that it will take a great deal of time before we can judge a research program to be pseudoscience. We can only say that a research program is pseudoscientific after we've seen how well various theories in the sequence perform. But it does seem like some things are just obvious nonsense, even if they're relatively new. For example, the time cube theory. If you haven't heard about time cube, just search it up online. It's a completely crazy crackpot theory, which was barely even comprehensible. It didn't even make any sense. I mean, it was just obvious nonsense from the moment it was proposed. But it seems like Lakatos would say, well, we can't say that, right? We need to wait and see how the theory develops before we can make the judgment that it's pseudoscience, and that seems unacceptable. A second problem is that the fortunes of a research program can change. Lakatos had to admit that a research program might degenerate for a while, but then start progressing. You don't jump off a highly successful research program just because it's hit a bad patch. Indeed, in principle, a research program could degenerate for hundreds or even thousands of years and then become progressive. Maybe one example here is atomism, which was popular in certain ancient Greek schools and then was rejected for thousands of years until staging a massive comeback at the end of the 19th century. Another example might be William Prout's program in chemistry. Prout held that all chemical elements have weights that are multiples of that of hydrogen, where hydrogen equals 1. And this program had a number of early successes, but it ran into a serious problem in that the atomic weight of chlorine was consistently shown to be 35.5. Of course, initially it was proposed that samples of chlorine were imperfectly purified, but as more purification techniques were developed, it just became clear that an integer value was not going to be achieved. And so it hit a serious rut and became degenerate. But then this program was later revived when it was discovered that all elements have different isotopes. Atoms are composed of protons and neutrons, and each element can have a different number of neutrons. It always has the same number of protons, but the number of neutrons can change. And in nature, every element has mixtures of the isotopes. And usually one isotope massively predominates, but sometimes, as in the case of chlorine, there is a substantial proportion of different isotopes. And so we end up getting a weight of 35.5. So, we can judge that a research program is degenerating, but we can't say that scientists shouldn't pursue a degenerating research program, because some ingenious scientist might turn it around. All philosophers of science can do is evaluate the present situation, but that evaluation can't lead to any practical advice. Now, in principle, this isn't necessarily a problem. In fact, we might think it's not really the job of the philosopher to offer any advice to scientists. And notice that although we can't issue practical advice to scientists, we can give advice to the rest of society. When deciding government policies, when adopting new technologies and so on, we should use the progressive research programs. Climate change is a highly progressive research program, so we have to adopt that when planning for the future. So for practical purposes, that arguably provides more guidance than Popper's falsificationism, which, as we saw, could only tell us that certain theories haven't yet been falsified. But recall that Lakatos wanted to show how science develops in accordance with rational methods. The problem is that it seems that he has to admit that switching research programs or sticking with a research program is not a rational matter, in the same way that switching paradigms isn't a rational matter for Kuhn. There's nothing irrational in sticking with a degenerating research program. So arguably Lakatos has failed to develop a rational methodology. Judgments of rationality can only be made historically after we've seen how the research programs developed. To push this problem a little bit further, consider the following case. Let's say that in the year 1900, a scientist decides to switch research programs, and let's call this decision X. Now, as of 1900, Lakatos's view is that we won't be able to say whether or not this is rational. But looking back from the year 2000, we can judge it to be rational. Now, this is a bit weird, and it looks like there are two possibilities here. So first, perhaps there's just no fact of the matter whether X is rational at 1900. It only becomes rational in the light of future developments. But this seems utterly bizarre. It seems to make rationality unreasonably dependent on luck. So a second interpretation is, well, X was in fact rational in the year 1900. It's just that there was no way for people to determine this at the time. There was some sort of epistemological obstacle. There was a fact of the matter, but we couldn't figure out what that fact was until many years have passed. Fair enough, but then we face the question of what exactly is this obstacle? Why exactly is it that the facts regarding rationality are hidden behind a curtain that is only lifted after many years have passed? Both of these options seem unacceptable. So there's a real problem with saying that we can't judge at the time whether switching research programs is rational, but that we can judge from a historical perspective, looking back over history, that the development of science is rational. Okay, another problem for Lakatos. We saw that Lakatos requires that progressive research programs must exhibit increasing novel predictions, and he probably inherited this emphasis on novel prediction from Popper. But are novel predictions so important? Consider, for example, the SETI research program, the Search for Extraterrestrial Intelligence. The hard core of this program, I assume, is something like the claim that extraterrestrial civilizations exist that potentially could broadcast and receive messages. Now, numerous theories of the nature and extent of extraterrestrial civilizations have been proposed, and so far, all of those that we've been able to test have been falsified. For example, one early theory proposed that there may be many communicating civilizations which communicate primarily using beacons spread out over the galaxy, sending radio messages at a specific frequency. This is a striking prediction, but it was of course wrong. It turns out that there isn't some massive intergalactic network of civilizations, or at least if there is, they communicate in some manner that we haven't realised yet. On Lakatos's view, it seems we have to say that SETI is a degenerating research programme. If confirmed novel prediction is what matters, then SETI exhibits a string of failed theories. But that seems unduly harsh. I mean, the main problem with SETI is just that the universe is so big and we have surveyed so little of it, and it just doesn't look fair to judge it to be degenerating at this point. Now, of course, we could alter Lakatos's theory to try to accommodate this. I mean, we might say, well, okay, it's not just novel prediction that matters. There are other theoretical virtues as well, and we discussed this in the last video. Virtues like explanatory scope, simplicity, fruitfulness for further research, and so on. And maybe the theories in the SETI research program increase these virtues. But if we take this view, we're going to have to say exactly how we weight each of these virtues and exactly how we can use them to judge whether a research program is progressive. I mean, we can't just do it based on gut feeling. Lakatos is supposed to be offering a rational methodology. So that's going to be quite difficult to work out exactly what to say here. Another problem arises when we consider the question of how do we specify what actually counts as a research program. Remember that research programs are demarcated in terms of their hard core of theory. But what counts as the hard core can arguably only be determined in retrospect. It takes time to develop a scientific theory. It takes time before we know what the important or central claims of a theory are. Consider Darwinism again. Darwinism faced a number of competitors, one of which was saltationism. The saltationists held that new species arise by sudden, large macro mutations. The slogan associated with the view was that the first bird is hatched from a reptile's egg. And that's a caricature, but it communicates the basic idea. Natural selection is not responsible for the origin of species. You don't get from, say, a raven-like bird to a jackdaw by gradual changes mediated by the action of selection over thousands of generations. Instead, it happens in a sudden leap in one generation. One of the most prominent defenders of saltationism was Hugo de Vries. Interestingly, de Vries often claimed to be a Darwinian. He saw himself as working within the Darwinian research program rather than competing against it. He would probably have said that the hard core of Darwinism was, say, the purely naturalistic approach to evolution and the theory of common descent. Today, we see de Vries as rejecting central claims of Darwin's theory, because de Vries rejected the creative power of natural selection. But there's no doubt that he did agree with Darwin on many points. So imagine if de Vries had been vindicated. Imagine if it had turned out that species do often arise through saltations rather than through selection. Well, maybe we would still regard Darwin as the father of this theory. Certainly that was how de Vries saw him. As another example, let's consider Darwin himself. I mentioned earlier how a kind of uniformitarianism was part of the protective belt of Darwinism. Today, we think that the history of life has been driven partially by big catastrophic events like asteroid impacts. We treat this as a relatively minor change. But for Darwin, uniformitarianism may have been of absolutely central importance. Certainly Darwin was very heavily inspired by the uniformitarian geologists. He may well have treated uniformitarianism as part of the hard core of his research program. These examples suggest that in specifying an unchangeable hard core, we might be manipulating history somewhat. The hard core will turn out to be whatever parts of the theory survive changes over the decades. But of course you can't know ahead of time what these parts are. And that will make it rather difficult for scientists to follow the injunction to protect the hard core by altering the protective belt. It's not really clear at any one time what the hard core actually is. Again, we see here how Lakatos's theory perhaps puts too much emphasis on purely historical judgments, because it seems to be that in order to specify what counts as a hard core, you need to take a historical perspective. You can only tell in retrospect what the hard core is, in the same way that you can only tell in retrospect what counted as a rational decision. So that might be another problem. Okay, I want to end with a suggestion that I thought was quite interesting from Peter Godfrey Smith in his Introduction to Philosophy of Science. Godfrey Smith suggests that we might combine the concept of the Lakatosian research program and the Kuhnian paradigm as follows. When a scientific field is born, research programs compete, and eventually one of them wins and forms a paradigm, and all scientists in the field agree on this paradigm. Then new research programs develop from this paradigm, one of which may win and become part of the paradigm, so the paradigm grows. Let's take Darwinism as an example. Historically, Darwinism was opposed by several other research programs. I've already mentioned saltationism, another was Lamarckism. This was the view that new species arise by inheritance of acquired characteristics. If you work your muscles really hard, you get big muscles, and the Lamarckians held that you could pass these big muscles onto your children. So changes to your body through your lifetime can be passed onto your offspring. And they held that was the mechanism of evolution, the primary mechanism. These different research programs were all competing up until about the 1930s. At that point, Darwinism triumphed, and it became a paradigm in what's known as the modern evolutionary synthesis. And since the 1930s, very, very few biologists have questioned the basic Darwinian claim. And it really does seem unquestionable at this point that natural selection is a central evolutionary mechanism. I mean, it seems certainly unquestionable that natural selection is the primary mechanism responsible for the emergence of adaptations, for the emergence of complex traits. But new research programs, which include Darwinism as part of their hard core, have popped up. Punctuated equilibrium might well count as a research program, competing against the phyletic gradualism program. I have a video on punctuated equilibrium, which you can check out if you want to know more about it. It's a theory of patterns of macroevolutionary change and includes some, it's also a theory about the nature of speciation and so on. And so it arguably counts as a new research program, but it retains the basic Darwinian core. Godfrey Smith's idea is that if punctuated equilibrium wins, it will then become part of the paradigm. So you'll then have a paradigm of the Darwinian core and the punctuated equilibrium core. And then new research programs will be budded off again. So we have a progression somewhat like this. We've got here along the top is T1, T2, that's just different times. So this is going through time. We have Lamarckism, Darwinism and saltationism along the left here. Darwinism wins, and then new research programs get budded off. So this is Darwinism plus punctuated equilibrium, and then this is Darwinism plus something else. And then let's say that punctuated equilibrium wins, and you can see that this central paradigm grows, research programs budding off. I mean, whether Godfrey Smith is, whether this is a correct view of science, I'm not sure, but I thought it was quite an interesting way to combine the ideas of Lakatos and Kuhn. So that's all for today. I hope you found that interesting. Thank you very much for watching. Goodbye.